ray tracing. In the modern gaming landscape, this term have become synonymous with expensive. But look at this. It is actually quite straightforward and not that many lines of C++ code. If we strip away the marketing and the hardware acceleration, ray tracing is actually one of the most elegant and simple algorithms in computer science, introduced in 1980. In fact, it is fundamentally simpler than the rasterization, which is normally used in games. Rasterization is about projecting 3D triangles onto a flat screen. Ray tracing is different. It is simulation of physics. It asks a simple fundamental question. If I trace the path of a light ray backwards, from my eye into the world, where does it hit? Let's build it in layers, step by step. To make a sphere, you might think we just draw a circle and move on. That would be wrong. I really don't need a circle, I need access to each pixel on the screen. With ray tracing, you shouldn't think, I want to draw a sphere. You have to change your mindset. Or reframe it to, I have a sphere somewhere in this scene, but there is no light, so currently I just have a black rectangle, the image plane. Let me add rays to see what is out there. Let us get to the code. But first, you need to understand how we see. Imagine that your computer screen is a window. You are sitting at a specific point behind that window, the origin 0, 0, 0. To figure out what color a pixel should be, we shoot a virtual ray from your eye through that specific pixel on the glass and out into the infinite world. We aren't going to use any libraries today, just pure math. We start with a helper struct, a 3D vector. It holds x, y, z and let us do math like adding vectors, normalizing them, or finding the length. Nothing scary. We run a loop for every single pixel on your screen, but pixels use integer coordinates like 0 to 920. Physics doesn't care about pixels, it cares about angles and relative space, so we convert every pixel coordinate into a range from -1 to 1. These are called normalized device coordinates, or NDC. -1 is the left edge, 0 is the center, and a +1 is the right edge. But wait, there is a catch. Your screen is likely wider than is it taller, probably 16 to 9 aspect ratio. If we map both width and height to the same -1 to +1 range, our beautiful sphere will get squashed into an egg. To fix this, we multiply the x-coordinate by the aspect ratio, which is width divided by height. And now, physics aligns with our display dimensions. If we map the x direction to red and the y direction to green, we get this gradient. This proves our camera is working. Every pixel has a unique direction vector calculated as the normalized result of pixel position minus camera position. Now, let's put something in the void, a sphere. A sphere is a perfect shape for a programmer because it is mathematically pure. It is defined entirely by a center point, C, and the radius, R. To see if our ray hits it, we use algebra. We need to solve for t, or distance, in a quadratic equation. The ray equation is origin plus direction times t, basically line in its parametric form. If we plug the ray equation into the sphere equation, we get this intimidating result. But don't panic, this is actually just the standard high school quadratic formula. ax squared plus bx plus c equals 0, or in our case, solving for t. Let's break down the coefficients derived from expanding the equation. The a term is just 1. Why? Well, because mathematically a is the dot product of the direction vector with itself. Since we normalized our ray direction, the length is 1, so 1 squared is, well, still 1. It basically disappears. The b term is 2 times the dot product of the vector from origin to center and the direction. It represents how aligned our ray is with the vector pointing to the sphere. The c term is the vector from origin to center, squared minus the radius squared. This term tells us about our starting position. If this is positive, we are outside the sphere. If negative, we are inside it. We solve it using the discriminant. Delta equals b squared minus 4ac. If delta is less than 0, the ray missed entirely. If delta is 0, we graze the edge. If delta is greater than 0, we have 2 hits, an entry point and an exit point. We normally want the closest positive t, the entry point. We apply this logic and suddenly the hits form a circle. See it? I didn't draw a circle at all, I just implied the existence of the sphere in the scene and told the rays to detect it. Anyway, I'm still talking about circles and spheres, but visually we still just have a flat colored circle. Let's change it and add some volume. To get volume, we need to know which way the surface is facing. We do this using the surface normal, a vector perpendicular to the surface at a specific point. For a sphere, calculating the normal is trivial. Take the point where the ray hit the sphere, subtract the sphere's center. We normalize the result of P minus C. This gives us an arrow pointing straight out from the core. We compare this arrow to the light direction using the dot product. This is technically called Lambertian shading. If they point roughly towards the light, the dot product approaches 1. The surface is bright. If they are perpendicular, it is 0. If they face away, the dot product becomes negative. Since light cannot be negative, we clamp it to 0. And suddenly, our flat circle looks like a ball. And that's it. Everything else really boils down to doing more things with the rays and the technicalities of the computation. Anyway, let's take it one step further. A floating ball is hard to judge. We need a floor. A floor is just an infinite plane. Checking if a ray hits a plane is simple. Is the ray pointing down where y is less than 0? If so, we can use similar triangles to calculate exactly how far along the ray we need to travel to hit the ground height. But we have a problem now. Sorting. What if the sphere is in front of the floor? A single ray technically hits both. It enters the sphere, exits the sphere, and eventually hits the floor. Which one do we draw? We solve this by keeping a variable called t near, or closest distance. First, initialize t near to infinity. Second, did we hit the sphere? If yes, and the distance is less than t near, set t near to the sphere distance. Third, did we hit the floor? If yes, and the distance is less than t near, set t near to the floor distance. That's it. Objects in front blocks objects behind. We simply remember the color of the object that was closest. The gray floor is dull, so let's make it more interesting. We look at the hit point on the floor. We take the x-coordinate and the z-coordinate and round them to the nearest integer. We can use the modulo operator or simple bitwise check. If the floor of x plus the floor of z modulo 2 is 0, we make it light gray. Otherwise, dark gray. This creates a perfect infinite checkerboard pattern with just one line of code. And finally, the finishing touch, shadows. In rasterization, shadows are a nightmare of shadow maps, bias artifacts, and resolution limits. In ray tracing, they are intuitive. Imagine our array hits the floor. We know the floor should be grayish, but is something blocking the light? To find out, we shoot a secondary ray, also known as a shadow ray. This ray starts at the floor hit point and looks towards the light. Here's a pro tip. We can't start exactly at the hit point, or math errors might make the ray hit the floor itself immediately. This is called shadow acne. We nudge the starting point slightly along the normal, point plus normal times 0.001. Does this new shadow ray hit the sphere? If yes, the path to the light is obstructed. The floor is in shadow, so we force the brightness to be darker. It is simple, accurate, and completely dynamic. And there you have it. From a simple vector struct to a fully ray traced scene with depth and shadows. The next time you see RTX On, you'll know it's not magic. In a nutshell, it's just a loop, quadratic equation, and a dot product. If you would like to see something similar, check out this video. It features a fully ray traced scene with several spheres, including a deeper dive into the mathematics. But what is really cool, everything there is happening in text mode. That would be all for today. If you want to see more in the future, don't forget to hit the subscribe button. Thanks for watching and ciao!